Swayam Prabha. Digital India. Educated India.
Okay, student. Today I will start again the wasp-free detection technique for the biosensor development. This is very important for point of care device development that I already mentioned in the last class. This class is really important how we can design a wasp-free sensors. So principle already I told. Now you have to understand all the optimization technology, like how much potential you need to apply, kind of chemicals you have to use. Like real sample analysis is really important, right? Otherwise there is no use if you cannot use your biosensor device for real sample detection. So how we can use the real sample? Like all the parameter you have to understand very critically. Then only you can apply your biosensor for point of care device development. Let's come. So today's main concept is the optimizations of the wasp-free biosensor. So all the parameters we can discuss, like as I mentioned, like potentials, chemical, their design, selections, everything. Everything I will discuss today, and also the design. So we can change like the your design of the sensor. Different design you can make for the wasp-free development. Let's start. So mainly the keywords is the wasp-free and point of care. This is the two important part for this lecture. See, here actually you can understand the story of the wasp-free. See, I think this biosensor like based on a enzyme, and if it is very close to the surface, like if you have the target and very close to the surface case, then you will get fast electron transfer rate because of close proximity, right? But proximity dependent electron transfer. So this is the main driving force, right, to determine the target and without target, right? If there is signal difference in the presence of target, in the absence of target. So here you can see like left hand side, this area is the with target, right? That I already showed you in the last class, right? And right hand side, in this case, without target. So this is mainly your signal S, and this is mainly your background B, and your goal to generate a high S by B value, right? This should be very high to make a good sensor, a very means a highly sensitive sensor development, right? This S by B value should be very high. So let's see the which parameter you should optimize. For example, in this biosensor I use FC, means ferrocene. So first you have to check the cyclic voltammetry of your electron mediator, like whatever reactions happening on the sensor surface, right? So first you have to check the cyclic voltammetry, the optimizations I am teaching you today. So that's a very important technique is the cyclic voltammetry. First you have to run a cyclic voltammetry of the chemicals you are using. So suppose here I am using the ferrocenes, this mediator, no? So let's check a cyclic voltammetry of ferrocene. Suppose it is showing like this. It is 0, here negative, here positive, right? In the x-axis here is the current, and y-axis is the potential, right? Unit is volt, current unit is microamps. See, your ferrocenes is oxidizing, suppose in this potential, right? So, to obtain a oxidation based very good biosensor, and if you want to measure by using chronoamperometry technique, so you have to apply more than this potential. Suppose this, so it is suppose it is plus 0.1, plus 0.2 and 0.3. So this is 0.3 volt. So for this biosensor, so you have to apply 0.3 volt, and your ferrocene will be oxidized, and it will form this enzymatic redox cycling, because you are using glucose oxidase enzyme as a tag, and glucose will react to form the gluconic acid, and your sensor surface will form the FC0 and it will be oxidized. So this is the enzymatic redox cycling will start, and you are applying here 0.3 volt. But you are, as I mentioned, that for the wash-free biosensor, finally your aim to develop a point of care device. So where we will use the real sample. You know, our real sample contain many species like glucose, uric acid, fructose, ascorbic acid. These all the things present in the blood, inside the blood. So in this applied potential, they also can be oxidized, right? So you have to keep in mind they should not oxidize on your sensor surface. So suppose that you just think that this right hand side, this part. So this is your background part. So at the beginning, if there is no target, so if you have interference species like ascorbic acid and you are applying 0.3 volt, then they will oxidize, they will create the high background. Your sensitivity, like signal to background ratio, will decrease. Your sensor will not be very sensitive, right? So you have to eliminate those interference species effect at the beginning. So you have to think how to eliminate. So one thing that you have to understand the interference is present in your real sample first. So you know our blood sample contain ascorbic acid AA. Then you have to first run a cyclic voltammetry of ascorbic acid in this potential window, where you are, this potential window you have to select, because you are running your all the ferrocenes or all the your chemical reactions going on, that you already took a cyclic voltammeter. In this region, you have to measure all the interference species effect. So we have seen that ascorbic acid can easily oxidize. It will form like this signal. At the 0.3 volt, it can easily oxidize. So what happened? Then your background current will be very high. Then you have to eliminate. So you can use ascorbic oxidase, one chemical that can react with the ascorbic acid. It will remove. So then you can we are actually increasing the number of the chemicals. Yes, because in this case ascorbic acid that can in the very low potential it can oxidize. You cannot avoid these ascorbic acid oxidations. So if you use ferrocene mediator, then it will be very difficult to avoid the ascorbic acid, because your ferrocene oxidizing in this region and you have to apply more than 0.2. No way. So this one you have to think. And your interference species also should not react with your mediator. Suppose if a ferrocene, they are reacting with your mediator, and if they can form a locally some another reactions, then they can increase also background, right? So other species also should not react with the redox cycling that already you decided. So this should be otherwise very, very slow or no reaction. Or your interference species itself, like uric acid, ascorbic acid, or maybe glucose, fructose, whatever you have, they should not react on the sensor surface, or you will get the high background. So these all the reactions should be slow. Also, as I mentioned, if you don't have target, your ferrocene and glucose oxidase glucose, that is also enzymatic redox cycling, that also should be slow, because they are far from the surface anyway. It will show the slow reactions, and you have to check how slow they are. Is they really slow and you are getting really low background or not? That you have to measure compared to signal, when they are very close to the surface. These two signal you have to measure. So left hand side the signal part, right hand side the background part, that you have to compare. Then only you can develop a highly sensitive wash-free biosensor. Let's come one example. A very low interference free a biosensor, how we can develop. As I said, the interference like ascorbic acid, uric acid, glucose, they can hamper your, so background can be increased. So how we can avoid, how we can make a low interference was-free biosensor. As I mentioned, when you use the ferrocins, it can oxidize the high potential. But if you can use some mediator who can oxidize at a lower potential, right? If you can oxidize in this potential, because your ascorbic acid is oxidizing in this region, right? So if you can apply lower than this potential, like this potential, then problem will be solved. That's why we can change the mediator. Means you are using enzymatic redox cycling here, but using another mediator. Instead of using ferrocin, here we can use the ruthenium then problem can be solved, because here we are applying lower potential. So which potential we can apply here? Here we can apply like 0.05 volt. So that's why potential optimization is a very important, crucial factor for development a was-free biosensor. So this point solved. So if we apply a lower potential, then we can avoid the interfering species effect. But still, see, this is the cyclic voltammetry. Just previous slide I also showed. Here this is the kind of data you can see. Like if you have the ascorbic acid C, this is the ascorbic acid CV, like this. But if you add ascorbate oxidase, then you see almost there is no oxidation. So you can use ascorbate oxidase. But still, if you see that no, ascorbic acid still is facing issue at the 0.05 volt, also still you are getting some current. So if you still want to minimize the background current, you can use ascorbate oxidase. Or otherwise, just take a cyclic voltammetry of the electron mediator. You may apply some other mediator whose potential is near, I mean this oxidation reduction potential in the negative region. So suppose you can apply in this side, very low potential, then you can avoid. Also like other interfering species, like uric acid, acetaminophen, they also can be oxidized on your sensor surface. But see the cyclic voltaminogram. So you have to check a cyclic voltammogram for those interfering species. See, uric acid, they are oxidizing around 0.4 volt. They started, and this area they fully oxidized. Acetaminophen, they are oxidizing very high potential. Then if you apply like here, like near zero potential, so near zero. If you apply this potential, then you can almost minimize all the interference species effect. So your washing free sensor become low interference washing free biosensor. Okay, so this is few parameters that I discussed, and another parameter I want to discuss now, that is oxygen effect. This is also really a big factor. It also can increase the background current, the oxygen effect, because your sample always contain oxygen, right? But if you use the glucose oxidase and this kind of enzyme, there is some side reaction with the oxygen, and it can cause the background current. So you can choose some level. With that level, oxygen effect should not be much fast. So here we use GPDase, glycerol 3-phosphate dehydrogenase, one enzyme where oxygen effect is very, very low. When oxygen side, this is the oxygen side reaction, that is very low, almost no. So if you select this kind of the enzyme, then side reactions become very slow, then background will be very low. Naturally, your S by B value will be very, very high. So you can make very sensitive was-free biosensor. Okay, so this also things you can keep in mind, means which level you are using and are they reacting with other interfering species. So oxygen is also one of the important interference species. Okay, see here some data, like we measure different concentrations of, see you can see different concentrations of the biomarker we measure. But one thing you see, like zero data and the different concentration data, their difference is not so high. In the was-free case, signal to background ratio cannot be too much high, because you already have your label in the same solution. The only we are differentiating just by optimizing different parameters. We are minimizing the interference species effect by applying some very good potential, also by optimizing some label that so that we can avoid other side reactions, and we are designing a redox cycling reaction so that when it is close to the surface, it will show the very fast reactions. When they are not very close, it will show the slow reaction. Okay, and we measure, you can see the calibration curve here we decided, and from here detection limit almost 10 picogram per ml, not the femtogram per ml, because as I said, here background a little bit high. So if you want to improve further, then you have to think about how you can still minimize the background current. Okay, there is still lots of scope you have for development of the wash-free biosensor. So you can again change this mediator, you can change. You can make so fast this enzymatic redox cycling, or some ECC based redox cycling also you can try, but you have to keep in mind so that these background reactions should be also slow at the same time. Let's come to another optimizations. Suppose you have the real sample you want to try, right? The real sample, suppose serum. So you have to compare that your serum sample that contains so many other species, and you are applying some potential in that potential region that other species should not hamper. How you can predict this? Just by taking a cyclic voltammogram, CV. So suppose minus 0.4 to 0.2 in this potential window, you can check a cyclic voltammogram in the real sample, and if it has many interference species, then it will show some oxidation peak, or it will show some abnormal behavior. So just PBS means phosphate buffer saline, it has nothing. Nothing means no interference species it has. So it is so only just see the background current. But now I measure the serum cyclic voltammogram, so it is showing little bit high, but almost similar. It means there is not that much interference species present in this potential window. But it has, but in this potential window it is not showing much effect. So I can try this potential window for wash-free sensor development. Hey, we also try like ruthenium hexamine with serum sample. So as I told, for development a wash-free biosensor, your mediator on the sensor surface, if you have mediator like M plus, it form the M, then Ma. So if interfering species also can react with this mediator, then the background current will increase, right? So that's why your mediator and serum both mixture also you have to check a cyclic voltammogram. See, it is showing almost the similar. It means there is not that much interference species effect in this potential window. Like this way we can determine. So like this we can optimize the several factors that your biosensor, whatever we are designing, is really useful for wash-free biosensor or not. Now come to the potential optimizations. This is a very important factor for determination, a potential optimizations, because finally we have to apply some potential, and at that potential other interference species should not be oxidized. So that's why. So as I mentioned, just like in this case, your main reaction is this one, right? Ruthenium hexamine, GPDH. What is this? Glycerol phosphate and glycerol 3-phosphate dehydrogenase. This one glycerol phosphate enzyme. This is enzyme substrate, and this is the electron mediator. So you have to take like a cyclic voltammogram with this whole reagent. So mixture that you have to take a cyclic voltammogram. Suppose it is showing like this. See, then different potential you can select, like one potential here. So in the case of ruthenium, you know, generally ruthenium showing not very high potential region, the peak. So in this case the axis will be like this. This is the 0, here minus, here plus. This is plus, this is minus. So in this axis this is current, and this axis potential. So we want to apply the oxidation base. So you have to apply more than this potential. So you have to select like 3, 4, 5 some potential. You can select like this potential, this potential, this potential, this potential. Let's try which one is the best potential for this biosensor. So we have tried like minus 0.05 volt, 0 volt, plus 0.05 volt, 0.1 volt. Then wanted to see which potential is the best for signal to background. So if you go back this biosensor, so at first you have to select the chemicals, right? This is called a control experiment for optimizations of the potential. You can see this is your actual biosensor, right? So in this biosensor case, if you have signal means your GPDA, GP, ruthenium, they are the all chemical, right? And if it is background means glycerol phosphate dihydrogenase will be very far from the surface. So mainly your background signal will be responsible because of GP and ruthenium, right? So GP and ruthenium will consider as the background signal it can cause, and GP, GPDA and ruthenium will consider they can cause the actual signal in the presence of target. Okay, so these three chemicals we will select and we will check different potential. We will check the current or charge. Again, GP and ruthenium, these two chemicals we will select, and different potential will measure the current or charge as per background. So that's why ruthenium and GP we will consider this one as the background. Ruthenium and GPDA we consider this reaction for the signal. Means this one just we said this is control experiment. Control experiment means at the very beginning, before fabrications of the biosensor, just we wanted to see the chemical behavior. So which potential I should apply. So this is you can think about just a bare surface without antibody coated also. You just think the bare surface. Let's run some cyclic voltammetry. Let's run some potential, and let's have some idea like which potential can be the best for this wasp-free biosensor. Okay, so now so ruthenium hexamen 3 GP GPDA I measured a cyclic voltammeter, and we selected 1, 2, 3, 4 like this way different potential, and see this blue one, this is the background. So because of negative potential we applied, so at the beginning it started slash oscillator reduction, then our oxidation started because it is not very positive. But if you apply some, like again if you go to the positive side, slowly you can see the background also increase and current also increase, and then 0.05 volt case also see the background also little increase again, but signal also increase quite a lot, and 0.01 ounce case also you also measure all the background signal. Then you have to calculate signal to background, this value 1, then this value signal to background is by B2, is by B3, and here also is by B4. Okay, so all the value we have to calculate. Now let's see which S by B value is the best value, highest value. So from here actually we have seen that at this potential S by B value is the highest. So then we can select, okay, let's fix this potential. This is the optimized potential. So this potential we can apply for wasp-free biosensor. Okay, so like this way we can optimize the potential parameter. So okay, now it is clear that we from this slide we can understand like which potential actually interference species can show their contributions, and in these slides we can understand which potential can be the best for the wasp-free biosensor development. Okay, so this is the main things. Now in this slide I'll show you some another technique, wasp-free biosensor, but another way to form the wasp-free biosensor. See, this is kind of like APTA sensor or DNA sensors, where one part we can tag with the electron mediator or electroactive probe, suppose methylene blue. So methylene blue, that is very highly electrochemically active. It can show the very good signal, very good electrochemical behavior. So we can immobilize when we can conjugate in one part of the like DNA or maybe in the aptamer. See, when you don't have target, then your aptamer or your DNA sequence such a way, so they are far from the surface. See, they are very far. And this ATGC sequence is made such a way so that when target, for example, here some toxin come in some specific region, it can come and bind in a specific region. Then it can fold, see, and bend towards the surface. So this electroactive probe will be very close to the surface, close to the surface. So this is called proximity dependent again, right? This is also proximity dependent. So what is the concept? At the very beginning your electroactive probe was very far from the surface, because there was no target, and we design like this way. And if target present, and we can design such a way so that there is a very specific part, and this part will bind with your target and it will fold, and your electroactive pieces come to the near to the surface. So then we can measure like anyway chronocoulometry, chronoamperometry, cyclic voltammetry, whatever you can measure. Or oxidation peak. So you can see the oxidation peak here this much, oxidation peak here this much, because it's close to surface, we are getting very high signal. So background case your oxidation peak like this, and signal case you are getting oxidation peak like this. So this much difference is there. So easily you can predict that how much target is present, because different concentration you can measure first with known concentration, then you have to make a calibration curve, and from this calibration curve you can determine the unknown concentration that I already taught you, right? So this is again I am saying another technique of WASP, because it is reagent free, because one electroactive probe already it is conjugated, you don't need any extra reagent here to determine your concentration of the target, right? So you just drop your target, your analyte, and if analyte present, it will bind, and because of this position change you are getting the signal change. That's why you don't need any extra reagent. That's why it is called a reagent free, washing free biosensor. It is also very good biosensor for point of care device development. No need any extra many expert persons, because we don't need any extra step washing. Okay, so this is the main part that we learned today. In this biosensor, we can optimize all the technique, and this optimizations is very important for the washing free biosensors. So first you have to run a cyclic voltammetry. Whatever chemical you are using in that washing free sensor, just run a cyclic voltammetry. From that cyclic voltammetry you will get lots of information, like which potential you have to apply, and in that potential you have to think like your real sample may contain other independent pieces, they are in that potential, how they will behave, that you have to think. So if you see that your interfering species also can react very fast, they can cause the background in that potential, then you have to change the mediator, or you have to change the reagent, something else, so that it can shift towards the left, so that you can apply lower potential, near the zero potential you can apply, something like this. So optimization is really very important. And real sample we learned today, because real sample handling is the final part, right? Whatever you developed in the biosensor, finally you have to develop some real sample, then it will be useful, it will come to the the end user. So real sample analysis, kind of reagent present in your real sample, that you have to know. Then you can check the cyclic voltammetry, like a blood sample contain glucose, fructose, lactose, uric acid, those cyclic voltammetry you have to measure, and then you have to check that whatever potential you are applying, that potential they are affecting or not. So that is very much important to validate your washing free technique. Okay. So anyway, so these two things we learned today, and next class again I will show you very many examples, some design, some new wash free biosensor and their applications for point of care device development. Okay. Thank you very much. Thanks a lot.